So as you can see, these are very simple equations, and they can be applied to a disk star at any distance. However, we can simplify them even further by considering only nearby stars, such that the distance between the star and the Sun is much, much less than the distance from the Sun to the galactic center. That is, let's do a local analysis and assume that d is much, much less than R0. That means that let's consider stars within less than 1,000 parsecs from the Sun. For these nearby stars, we can expand the angular velocity in Taylor series around R0. And we can ignore the second order term. So I have an expression for omega minus omega naught. Omega naught being omega measured at R0 is the derivative of omega with respect to r measured at R0 times the distance r minus R0. Now, if you substitute this expression for omega minus omega naught into the radial velocity, then you have an expression for the radial velocity in terms of d omega dr. Now, if you are at a distance d that is very, very small, so this would be r, and this is R0, and this is the distance d, much, much less than either R0 or r, and this is the angle L, then you can approximate that the distance R0 minus r, which is this distance in here, is then equal to d times cosine L. So in the equation for the radial velocity, you can substitute r minus R0 by minus d cosine L. And now we can use the trigonometric identity that twice cosine of an angle times the sine of the angle is the sine of twice the angle, so that this becomes more compact. So now we can define a constant a that is equal to minus R0 over 2 d omega dr at r measured at R0, R0. And with this substitution, then the radial velocity is AD times sine of twice the galactic longitude. This A is the first Oort constant, and is a measurement of the shear, the omega dr. That is, it's the degree to which the disk of our galaxy does not rotate like a rigid body. The equation for the radial velocity implies that the radial velocity of nearby stars on circular orbits will be 0 when the galactic longitude is either 0 or 180, but also when the galactic longitude is either 90 degrees or 270 degrees. So if you measure the radial velocity with respect to the local standard of rest for a number of stars as a function of their galactic longitude, you're going to find a sinusoidal curve with amplitude being given to a times d, the mean and the distance. If you make a plot like this is what you get. So on the left-hand side here, you see a plot for Cepheid stars with mean distance about 2.3 kiloparsecs. So if they're all at the same distance, then you have a measurement of A. And on the B, on the right-hand side plot, you have the same plot done for early type B stars with mean distance about 2 kiloparsecs. The plot for the Cepheids yields the value for the A constant to be about 14.8, so about 15 kilometers per second per kiloparsec. Because A is a measurement of the differential rotation, a non-zero value for A that comes from Oort's analysis was the first definite evidence that our galaxy is in differential rotation.